Any sufficiently advanced technology is indistinguishable from magic.
All right, everybody, it is a pleasure today to welcome Dr. Delilah Gates. We've had on mother-daughter combinations. We had on Andrewian and Sasha Sagan, mother-daughter duo. And now I can say we've had on father-daughter duo, Jim Gates, and now Dr. Delilah Gates. As of about 3 weeks ago, as we're speaking here in May, Delilah, a brilliant scientist, became a PhD at Harvard University and is moving in the fall to Princeton University, not far away. And she is going to tell us about the fascinating universe of black holes and their electromagnetic signatures and ways that we could possibly observe them. We're going to go deep. We're going to start broad, but you and the Into the Impossible audience are some of the deepest and brightest in the known universe. So Delilah should not fear to go as deep as possible. And you're in for a treat because she is one of the foremost exponents, proponents, and experts in the world of the universe, really, of these mysterious, magical, mystifying objects known as black holes. So you're going to see a real kind of insight into research at the forefront of astrophysics. And so now I turn it over to this brilliant colleague, Delilah Gates. Take it away, Delilah.
Wow, thank you so much for having me. That was such a magnificent introduction. I feel very humbled to have such things said about me. So, as you mentioned, I just recently defended my PhD at Harvard, and my thesis was on observational signatures of black holes, which, like planets, can be spinning. And in particular, we know that there's LIGO, which can observe in the gravitational waves, but we also can get electromagnetic signatures, that is light, from the matter that's accreting onto the black hole. And so that really is the realm of which I study. And so let me start broad with a couple questions. Namely, we are lucky now to have this image of M87 from the Event Horizon Telescope collaboration, which is the first image of a black hole near horizon region created from observational data. And it's a very blurry image, but it's a remarkable feat of technology because of the angular resolution that is needed to create such an image. It's very tiny on the sky because of how far away this black hole is from us. And so, but if you were to look at an image like of a black hole, and we now have one from data in the close near horizon region, but we know how to simulate them. If we're looking at images of a black hole, of course, you might wonder, how do I know this image is a black hole? Or in particular, more detailed, how do I know that what I'm observing is a black hole, and what are the distinguishing characteristics of it? How fast is it rotating? How massive is it? If it's rotating, we could be viewing it off the spin axis at a various angle. And so these are kind of the questions I try to dive into with my work. So to start, let me kind of go broad. So early on, the idea of a black hole was actually perhaps first proposed in way back in 1783, which is perhaps surprising, but it came from the simple thought experiment of philosopher John Mitchell when he asked, what if you had a star that was so dense that its gravitational pull was such that the escape velocity from the black hole was the speed of light or greater? And this obviously today invokes in us the idea of the event horizon. But the idea kind of died out. We didn't have the mathematical machinery. We didn't think about space-time curvature yet. So it wasn't until Einstein in 1915, when he gave us general relativity, that we were really able to make headway in black holes and studying them mathematically. So it turns out if you describe a black hole mathematically, you describe the shape of space-time, which has to have an event horizon somewhere. And there are different solutions to the Einstein's equations that have event horizons in them. Einstein never thought someone would be able to describe the shape of a space-time that would solve his equations of general relativity, the Einstein's equations, but it turned out very quickly the first one came along from Schwarzschild, and this was just a non-spinning, non-electrically charged black hole. Soon after, discovered by several people over the next couple of years, discovered and rediscovered, was the case of a non-spinning black hole that's charged. Breaking spherical symmetry just down to axisymmetry was hard. Like I said, black holes can spin. We see planets spin all the time, stars. And so just like that, black holes themselves can spin. And it wasn't until 1963 that Kerr gave us the idea of the spinning black hole that was non-charged. Then it was not too difficult to jump, where Newman gave us the solution that describes the spinning and charged black hole. The reason it's perhaps nice to think of this spinning charged black hole is because this is the most general axisymmetric black hole we can describe that is asymptotically flat. The reason we want asymptotic flatness is because that means far away from the black hole, space looks flat, and so it would be relevant to our universe. But it turns out charge, mass, and spin are the three things that could, in principle, describe a black hole, but we actually expect that real-world black holes aren't electrically charged, and this is because they don't exist by themselves in a vacuum in the way that they do in the idealized solutions to Einstein's equations. They actually have matter accreting onto them, and so they could easily neutralize themselves just by absorbing charges, particles of the opposite charge to themselves. So this tells you a little bit about the history of black holes and why Kerr black holes, or specifically the spinning case, non-charged, are what we want to study when we think about the astrophysical black holes that we're going to observe, or that we're starting to be able to observe in the near horizon region, thanks to technology like the Event Horizon Telescope. So this solution, let me just flash it for those who care, but don't be intimidated by the equations, please. This is just the mathematical description of this shape of space-time, where we have this asymptotically flat kind of funnel shape, and it's spinning about a rotational axis. And so the two things that describe it are its mass and its angular momentum. And so this seems to say that black holes are deceptively simple. You would seem to think that all black holes, at least in general relativity, so not considering quantum gravity, are just described by two parameters: how fast they're spinning and how massive they are. It must be perhaps then easy to take an image of a black hole and then understand or mine from features in the image what the spin and mass of the black hole are. So this goes to then the idea of simulating black holes. And so the first ever simulated image of a black hole came from Luminet in 1979. And in this case, it's a black hole with a thin accretion disk around it that's non-spinning, so a Schwarzschild black hole. And one of the things that we notice is we get kind of this dark depression in the center. We have this bright ring around it, etc. And this was done back in '79, but today we do them a little more sophisticatedly using general relativistic magneto-hydrodynamical models.
When you see the images, or you see these simulations, or even the data from the Event Horizon Telescope, are we visualizing here the black hole, the event horizon, or what's called the light shadow? I've heard there are differences between these different concepts.
This is a really good question. So let me go to my next slide because it is a sharper image and it might be a little nicer to look at. So here on the left we have an image from one of the observing days that the Event Horizon Telescope collected data from the near horizon region, the light around M87 star, the black hole in the center of the galaxy M87. And here's a general relativistic magneto-hydrodynamical model. And so the question is, what exactly are we seeing? So there are a couple things. The first thing is we generally a generic feature we get in these images of black holes is this bright ring. And the reason for this bright ring is actually particularly interesting. So when we think about black holes, and we solve the equations that tell us how light travels between 2 points around the black hole, it turns out every point in the geometry is in fact connected to an observer. If you take 2 points between where the light is emitted and an observer, there are infinitely many paths that actually connect the observer to the source point. And so this actually implies that you get an infinite number of images of the source emission around the black hole. And in fact, what we can see is the reason for this is there are these bound orbits around the black hole. These bound orbits exist in a region outside the event horizon, in what we now call the photon shell. And so there are a particular set of radii around the black hole where we can get photons on these kinds of bound orbits, like shown here. In fact, this is an example from an applet that you can play with online at Leo Stein's website, due2symmetry.com. I suggest everyone go play with it. It's very fun, and you can look at the shapes of the bound orbits that photons could travel around a black hole. And so we have this region in which the black hole, the light around the black hole can orbit in perfectly circular orbits, but it turns out these orbits are unstable. So this means if we were to perturb them just slightly, the photons would travel many times around the black hole before either spiraling into the black hole or going off to infinity. And you can actually parameterize the number of times the light, the photon wraps around the black hole before reaching its destination in half orbits. And it is in fact this that leads to the multiple images you get of the black hole. One of the equations describing the motion of the black hole describes where its theta position and its r position, the radius and the angle theta. And so here is an example. You have a point in the disk, and you have an observer. You can have light that comes from it directly with an extra half orbit around the black hole completed, or with two, and technically you get an infinite tower. But in particular, you can map exactly where kind of a locus in the sky of where these points want to pile up. And it's so the more and more highly lensed, wrapping around the black hole multiple times, images of the black hole actually tend to stack up together, kind of on top of one another almost, to give you kind of this bright ring we see. But this is one thing that is apparent in general relativity, but this doesn't quite explain the image we have from M87 star at this resolution. Here's an example of just taking the GRMHD model and blurring it. And you see it looks really similar to the image we have from the observed data, which is good, but we're not necessarily sure from this resolution that what we're seeing are the demagnified images that are of the same source being stacked on top of each other, being blurred. A lot of the emission is, of course, just the direct light as well. You can kind of see this kind of background, very red looking in this image, just general, that's just the direct image of the source emission. And then we get images stacked on top that get more and more focused on this position in the sky. And so it's not necessarily apparent from the data we have now at M87 whether we've actually gotten a lot of flux from the more highly lensed images of the source emission. So there's still more work to be done. So what are we seeing? We're probably seeing something like this that's blurred, but we haven't quite been able to pull out enough features to exactly say that we know we've captured a lot of light from the lensed images of the more highly, the images from the sources that wrap around multiple times, except for just the direct. But we are, if we do assume that it comes from such a model like this, we can, based on just blurring a model like this or several models like this that could match or look close to M87 once blurred, we do locate this ring, even in its blurred form, to get an estimate of what the mass must be. And so, but in particular, the details of how the light stacks up should also give you information, say, about the spin of the black hole. And we definitely haven't done enough. We don't have a high enough resolution yet to be able to definitely say we've seen these higher lens images, and thus could constrain the spin of this black hole.
Mm-hmm.
Another thing is, you might notice there's kind of this dark depression in the center, and you might think that this is also something that, if we had a sharper image, would be easy to say what this is a map of, but it's actually not quite that simple. The exact position of that inner dark kind of depression compared to the bright ring does depend heavily on your details of the astrophysics, where the matter is around the black hole, how much it's emitting. Is the matter that's emitting the light mostly radially plunging into the black hole, or is it spinning around the black hole a lot, very circularized? So even this inner shadow, its details are somewhat of an astrophysical question, not just a general relativistic.
Can you say something about the challenge to solve these equations in GR? We're usually presented by, as advanced undergraduates. When I teach cosmology, I might expose them, if I do, to the Friedman equations, how we derive them from GR, how in principle you can get them in the Newtonian limit from the Einstein equations. Maybe as a teaser, I'll show them what they'll learn in graduate school. The Einstein equations, very simplified form. You're talking about solving these in magnetohydrodynamics. These are very challenging equations to solve. Can you talk about how you actually solve these on a computer? Like, how do you constructively do it? I'm an experimentalist, so I never solve these equations, even using paper and pencil. But first of all, what makes them so challenging? And then, how can a computer even approach solving these and provide images like the simulations that you work on?
So I actually myself don't do general relativistic magnetohydrodynamical models. I generally work very much in the realm of looking at kind of pen and paper stripped down toy models, doing exact calculations as analytically as possible. So I don't generally myself do general relativistic magnetohydrodynamics, but I can tell you how it works. So the first things to think about, there is the modeling the accretion, and that's really where the GR MHD is king. This has to do with taking the matter and modeling as a plasma that has turbulence and all these things, and magnetic fields that's wrapping around the black hole and emitting light. But then, of course, you can say, I have this disk and it emits light, but the question is, where does it end up? The question of where it ends up and appears to an observer is actually is actually something that's really nice in the case of the Kerr geometry. It turns out, so in general, let me talk just a moment about how we describe an image of a black hole like the ones I've showed, versus what the light is actually doing. So in general, you can think of, a black hole or some other massive object that will lens particles as they travel around it, and the observer will collect them from the light that hits it from different angles. To mimic what we see, since we're used to living in a flat space, what we do is we do this idea of thinking I would assume, the way my brain puts images together, that I project the light straight back onto a plane. And this kind of mimics what we see. It turns out, to describe precisely the paths around the black hole that light takes, in the case of the Kerr geometry, is actually it's simple compared to a lot of generic cases. And by what I mean by simple is that the motion of the particle actually depends on some specific conserved quantities in the space-time. There's the energy of the particle, there's its angular momentum, and then it also has one more conserved quantity called the Carter constant, which it doesn't have as nice a physically intuitive description as angular momentum or energy, but in the Schwarzschild case, you can think of it as being related to not just the angular momentum around the spin axis, but the total angular momentum that the particle has. And so in the case of the Kerr geometry, it turns out it's quite simple to say exactly what the particles do. Like I said, their energy depends on these specific equations, but it turns out further that the equations are completely integrable, which means that you can write a set of integral equations that use elliptic functions that relate any source position to any other point, observer position. And so these have been known for a long time, and you can then you can just take these integral equations and throw them onto a computer. So if your light is emitted from near the black hole, from this disk that you've modeled with GRMHD, you can then just ray trace. So you can just you know exactly where your observer is, so you know the kind of paths that the light will take between the observer and the source, and you can just really integrate. Numerically, it turns out you can actually do it completely analytically, but sometimes that's a little challenging and time consuming. So you can do it numerically or analytically, and you can just literally trace the paths that the light's going to take.
Oh, wow.
In the case of how this is done in practice, let me also mention, you might say, if I just look at the source and then trace all the paths that the light can take, a lot of the light is not going to hit my observer, right? If I look at a point near the disk, the light's just shining out from all directions from a single source, and only some of them are going to go hit my observer. So in practice, what we actually do is the opposite. We trace from the observer 2 different points in the disk along the geodesic, or the path that the light takes. And we just look at our image screen. Let me do the example. Let me just pull back up this guy. So we might say, okay, let me pick a point on my screen here or here. And I'm going to say, how bright should this point be based on my emission model? So I say, this point, the light arrives at me from this angle. I know then what that means, exactly what its angular momentum and Carter constant will be, and I could know its energy. And so then I trace back along the path from the observer into the geometry, and every time along the path that I cross matter, I load more brightness onto my pixel. And so this is known as radiative transfer, the radiative transfer equations. You can also include details of not just adding light to make the pixel even brighter every time you cross matter. If the disk has some absorptivity, you can also subtract some of the brightness depending on where it crosses the disk as well. And so that's how we build these models after we have described the emission using the general relativistic magnetohydrodynamics.
Okay, great.
So in particular, though, describing general relativistic magnetohydrodynamics is complicated. And like I said, there are some things common about these issues in images, like the bright rings from all these different emission models. But there's also some things that vary, like, for instance, exactly where that dark depression is. You have things in common. You definitely get a bright ring. You definitely get a dark depression. But where is the edge of the dark depression, etc., is kind of complicated. And so my work particularly focuses on thinking about the things that are similar in the image, all the images of a black hole. You could think, oh, it's hopeless. How will I ever know what black hole I'm describing? If I can change the spin and still get very similar images, if I can change the astrophysics and still get very similar images. But the fact that there are these commonalities between the images actually suggests kind of a separation of the different types of features in the black hole images. You can look at the features that are universal, like the fact that you will have a bright ring. And these are mostly driven by the general relativity, or the fact that you get multiple images stacked on top of each other. That's driven by the general relativity. And then the features that vary with the accretion model really are driven by the astrophysics. So in my work, I try to really target the features that are universal and use these to pick out ways we could mine information from the images, from the observations of black holes, without having to be aware of what the astrophysics is.
Also, and I've noticed in your papers, you focus also on extremal black holes. Am I pronouncing that right?
Extremal.
Extremal.
Good. This is exactly what I wanted to say next.
Okay, great. Yeah, I was hoping you could explain to me what that is, because I read it in your papers and I'm not 100% sure.
Since we're gonna pick out, since we want to pick out the features that really are driven by the general relativity, we want to think about the ways that the space-time of a black hole is unique. One I already mentioned for you was the fact that you have these bound orbits and then can get multiple images of your source. And the other thing is, another property that I like to exploit is for the case of the high-spin black hole. And this is what we call an extremal black hole. Their high-spin black holes just mean we're taking the spin of the black hole up to its maximum. So let me back up for just a moment and flash the metric for you once more. So like I said, this black hole's, the details only are described by its mass and its spin, angular momentum around its spin axis. In particular, we use this parameter A to describe that. So if the angular momentum is J, we have this spin parameter A that is just equal to the angular momentum around the spin axis if we multiply it by m. In particular, one of the things we notice about the space-time is it has an event horizon, whose location also depends on those two parameters, the spin and the angular momentum. But in fact, there's a bound on how fast black holes can spin. Kerr black holes can spin. And this is called the Kerr bound. And the reason for this is if you spin the black hole any faster than this, you would not have an event horizon. And then you would have a naked singularity. We think that's probably unphysical. There's the cosmic censorship conjecture. But in addition to that, we also think that physical processes probably prohibit us from taking a black hole that starts below the Kerr bound and ever actually getting exactly to its maximum spin. And there have been attempts to quantify exactly, based on physical processes, what that bound would be, the most famous of which is the Thorne bound, which is 0.998% of maximum spin. It's not actually sure if this is the right bound. There were some assumptions like a thin disk model and whatnot made to derive that bound, but it does seem that we probably can't spin black holes all the way up to this bound, but it does look like from a lot of experimental evidence that we can spin them pretty close to this bound and that a lot of black holes are probably very rapidly spinning. And so this is a motivation for why we care about this particular property for high spin black holes or extremal or near extremal black holes. Extremal just means at its maximum, at its extreme value. And so in particular, what happens when we spin the black hole very fast is it turns out the funnel part of the geometry gets really, really elongated. And in fact, in the limit that you go actually all the way to the maximum spin, it technically would get infinitely long. But an interesting thing that happens as if we zoom into the horizon, is it turns out this region that is this long throat region of the black hole actually has more symmetries than just the general Kerr geometry. So the Kerr geometry is stationary, which means it doesn't change in time. And it's axisymmetrical. It means you can rotate it about the spin axis of the black hole and it will look exactly the same. Turns out for the region close to the horizon of the black hole that is described by this, in principle, infinitely long or elongating neck as we spin the black hole up, or elongating throat of this geometry, there are two more symmetries that develop, and it turns out that we can exploit these symmetries for the case of high spin black holes, or to say something about what would be some observational signatures specific to black holes that are spinning very close to the maximum. One of the interesting symmetries, one is very hard to describe, but the other one is called a dilation, and it basically tells you that the physics at one radius in this throat part of the geometry where you're close to the black hole, it looks almost like a perfect cylinder. In this region, it turns out that the physics at one radius along this cylinder should be the same as the physics along another part of the cylinder. And so this actually kind of has interesting implications, and in and of itself, this kind of dilation symmetry that you have. And so from understanding those two things, understanding the bound orbits and understanding these extra symmetries that develop near the horizon of a rapidly spinning black hole, these two unique properties of the Kerr geometry allow me to look for or pinpoint signatures that would show up by being imprinted on the light that we observe from around the black hole, to say things independent of most of the astrophysical details. What are some hallmarks telling us we're looking at high spin black holes?
For reference, Delilah, how close to extremal are the black holes that LIGO typically finds, like in terms of spin or mass or the EHT, tens of million solar mass black holes? How could you say what their spins? I mean, I know we don't have great limits so far, but do we have any ideas?
So,
or is that the
it's actually so in the case of M87, we don't have necessarily a great spin estimate. There are some papers claiming it might be as high as 98% of extremality, but it's very unclear. And in fact, this is one of the motivating features for upgrades to the Event Horizon Telescope, or to extending our Event Horizon Telescope-like observations to include a telescope in space. The reason for this is I'm not an expert in this, but we use interferometry to image these black holes. So really what we observe is the Fourier transform of the image, like the one I showed you, that blurry image of the near horizon region that was collected from data. But we really observe this in kind of Fourier space. And the details of this depend on, of course, the size of basically your satellite dish, but instead of a single satellite dish, what we really do is use two different points right now on the Earth's surface, basically turning the whole diameter almost of the Earth into the length of the satellite dish. And so we can use different length dishes to get different resolution, to increase our resolution, or different lengths between our two baselines, different length baselines. And so this is a motivation, the fact that if we get higher resolution of the near horizon region of this black hole like M87, or our own galactic center, Sagittarius A star, if we can get higher resolution and really tease out details like the fact that you would have the repeated images on top of themselves, and where it would be located, or conversely, like I said, there are these multiple images, but of course there's a time delay between, like if you've got a flare, there's a time delay between the first image of the flare as seen by the observer and the second image that comes from the photons that wrap around the black hole more. And so if you can also think about the time delay, and making correlations between the time delays, if you had higher resolution, you would be able to tease out information about what the spin of M87 is. M87 is. So this is part of a big piece of motivation for extending the EHT, or the next generation EHT. So I guess I can, as a final thing, say exactly what are some of the observational signatures I've studied. I won't go into great detail about them, but maybe I'll flash them on the screen. So one of the ones is going to particularly depend a lot on the fact that the black hole is a high spin black hole, and what we do is we look at the polarization. Recently, the EHT released polarization data from M87 star, which is amazing and wonderful, and it gives us a hint about what the magnetic fields should be like around the black hole. And so in the case of a high spin black hole, one of our proposals was we notice in simulations that once you've time averaged an image, that often the image that you see from the light around the black hole has the same symmetries as the space-time. In the case of Kerr black holes, this means once we've time averaged, the light around the black hole looks very axisymmetric. And so we said, what if we assume that this inheriting of the symmetries is true for all space-time symmetries? In the case of the high-spin black holes, light from near the horizon then should have imparted on it these extra symmetries that the near horizon geometry has when the black hole is maximally or near maximally spinning. And so if we constrain what the polarization should be when it's emitted near the black hole with these symmetries, and then use our geodesic equations to transport it to a faraway observer, what might we see? And so in particular, we might see something like this. This outer red curve that I'm showing you is what's known as the critical curve. You can think of this curve as being where in the sky exactly the bound orbits would map to. The photons traveling on those bound orbits would map to. In the case of, a really easy way to think about it is if you were to backlight a black hole was just by itself, nothing spinning around it or accreting onto it, but you backlit it, what silhouette would it cast? And in particular, it would cast a shadow that would have a dark region on the interior and then be bright all outside of it. Of course, this is not a physical thing because black holes aren't backlit and they can have sources anywhere around them, but that's kind of intuitively what this critical curve is. And it turns out if we were to consider all the light from this near horizon region of these maximally spinning black holes, we'd get these polarization patterns if they were constrained by those near horizon symmetries that only would fill up this region that's inside the critical curve, or would be the dark region if we were to backlight the black hole. And so the polarization in these plots is shown in black, and the different colors, the blue, yellow, and green, just corresponds to how many times the light wrapped around the black hole before reaching the observer. So it's not, you wouldn't actually see any of the colors like that. It's just for our own kind of image. And in particular, in the case of something like M87 star, it would look something like this. Another observable that I've thought about is, what is, if you had a disk around a black hole that was spinning, what is the maximum blue shift that the light that you observe from around that black hole would be? In particular, we can think of a black hole, say, with a very thin disk. For a toy model we did a thin disk that's in the equatorial plane of the black hole. We can think about all the light around the black hole being emitted from orbiters, from particles that are orbiting the black hole on stable circular orbits. And then we can ask, what of all the light that was emitted, what would be the most blue shift of the light we could get? And in fact, this is really relevant because this is already a method used to constrain the spin of black holes. Here I've just shown just the direct image of a black hole's disk, where we've colored the disk by the blue shift or red shift that you would observe. And this is relevant because this is actually already used as a method to constrain the spin of black holes. You can think of, if you know what the line emission, say, from an element in the disk is going to be, we think they tend to have a lot of iron, so we could target a specific frequency in iron's emission spectrum, say the K alpha iron line, which is very prominent. And we can look at how the whole single emission gets broadened. Some of the light will be blue shifted, some of it will be red shifted, depending on where it's emitted in the disk, because of the motion of the particle in the disk relative to the observer. And then there's also an overall redshifting from the gravitational redshift as well. But it turns out the gravitational redshift is not so big that you never get light blue shifted relative to the frequency it is emitted at in its own rest frame. It turns out very close to the black hole, the particles orbiting the black hole are moving at such relativistic speeds that they'll impart enough blue shift with their motion that the overall frequency you would observe would actually be blue shifted relative to the emission.
So it's never gravitationally redshifted.
Right. Some of it will be, and you actually get kind of broadened profiles of emission. that looks something kind of like this. But in particular, we were just asking about the most blue edge. These are some models from a code called Reline, which takes the model I described before, thin disk orbiters on the emitters orbiting on stable circular orbits in the equatorial plane. And you see, of course, the whole iron line, K alpha, it's marked here and here, that you get these broadened profiles, but these profiles vary dramatically depending on what angle you're observing from and the spin of the black hole. And so we were really trying to see how much of the information was just carried by the most blue shifted edge. And it turns out you can actually kind of analytically describe what happens for all different spin cases, analytically or semi-analytically. And so this is kind of what we get. This right here is blown up here. This box is blown up here. We have in the different colors the different spins. The black is an approximation that fits for when you're viewing at angles close to the close to the spin axis. And then in the high spin case, it turns out we have also this orange dashed line. I can go into more details if people care, but this is the theoretical limit of exactly what the highest blue shift you could get is. And you need to understand, to analytically calculate this, you need to understand the near horizon geometry as you spin the black hole up. But basically what we find is that the spin of the maximum blue shift of the black hole for if you're viewing close to the pole, it gives you very good information about what angle you're viewing the black hole from. It doesn't tell you about the spin. But if you're observing closer to the equator of the black hole, say like we are to our own galactic center, then it tells you a lot of information of being able to constrain the angle which you're viewing the black hole from and the spin. And if you already have some angular information about what angle we're viewing the black hole from, say a jet, then it really becomes a tighter constraint just on the spin. And so these are a couple of the observational signatures that we've been able to characterize. And I guess I will mention the last one that I have thought about for my thesis isn't as tangible as the other two because it just talks about light from a disk around a black hole that's again made of these circular equatorial orbiters. But the case is now we have light that could fall into the black hole or just escape to infinity. But we don't particularly say where at infinity. So this isn't quite a real observable in that we can't put a bunch of detectors all around a black hole yet. We don't have that kind of technology. But I use the term observable loosely in that I mean it definitely talks about light that reaches the faraway observer and doesn't get captured by the black hole. And in this case, in particular, we can describe two features. We can say if light is traveling on one of these circular stable orbits around, if a massive particle that's emitting light is on one of these stable circular orbiters, what percent of all the emission it releases, if it's just isotropically emitting, escapes to infinity versus being captured. And it turns out even down to the innermost stable circular orbit, even in the case of the most rapidly spinning black holes, more than 50% of the light will always escape from these kinds of orbiters, which seems surprising because you say, oh, as you spin the black hole up, the innermost stable circular orbit gets really close to the horizon. You would think a lot of its light would get captured, but it's the case that more than 50% will always escape. And then also we could say of the light that escapes the celestial sphere, what would, for all the observers on the celestial sphere, what would the profile of the light look like in terms of redshift? And in particular, there's a nice image of what the black hole does to the flux profile. In general, you would say the flux would look linear, but the light that gets captured by the black hole is these little bites that are literally taken out of the flux. So the black hole imprints these bites on the flux curve. So these are the kinds of things that I think about when I think about black holes, is really trying to tease out information that will let us say what the black hole is, how fast is it spinning, how massive is it, what angle are we viewing it from, without having to, do these expansive searches where we compare it to a lot of astrophysical models because we don't know what's actually going on near near a single black hole that we could observe in the sky one day.
Oh, that's brilliant. Thank you so much, Delilah. This is excellent.
Any sufficiently advanced technology is indistinguishable from magic.